Hello and welcome back to this course. So last class we were going through the fuel cell construction, wherein we discussed that it's a device that houses this electrolyte at the center, and it is basically sandwiched between these two electrodes, that is anode and cathode. This assembly is called as membrane electrode assembly. So let me write this up. So assembly, which is basically also abbreviated as MEA. And this assembly, as we can understand, it's the heart of the fuel cell, or when it comes to electrolyzer, it is also equally important. So all these reactions that we have seen so far, they all take place in this the electrode and this electrolyte, and that is why the function of, and rather the characterization or the fabrication of this assembly becomes of paramount importance. We also have this bipolar plate. So let me quickly show how the electrons flow. So once we have this hydrogen getting oxidized at the anode, protons pass through this electrolyte, whereas electrons, as we can see here, the electrons they jump back in the towards the gas diffusion layer. From gas diffusion layer, these electrons come back to the monopolar plate in case of single cell, or it's a bipolar plate in case of stacks. And from this plate, they are again taken towards the current collector, and from current collector they reach the external circuit. That's where we get current, and through this external circuit they again enter the current collector on cathode side. Once they come on the cathode side, these electrons again jump back to the bipolar plate or the monopolar plate of the cathode side, and from this bipolar plate again get into this gas diffusion layer of the cathode, and from gas diffusion layer to the catalyst layer of the cathode, where this cathodic reaction takes place. So as we can see, in some cases the end plate is kept as an option. We can have this end plate, or we can also treat these bipolar plates as the end plate itself. So we can in stacks, typically we can have the end plates at the end, and the rest of the bipolar plates are arranged in appropriate manner. So let's go ahead and see how the actual fuel cell looks like. As we can see here, so this is the typical fuel cell that is available in the market, and as you can see, we have these nuts and bolts. They are basically used to clamp the entire cell, and these are the end plates, these ones, and these two, the copper plates, as we can see, these are the current collectors, and the entire assembly is basically placed at the center. So let me open this up to have a better understanding about the fuel cell. Electrolyzer also looks of similar, and most of the times it looks very similar. The only change that we can expect in case of fuel cell and electrolyzer is the catalyst and the gas diffusion layer. This is the end plate, and this is the gasket, which is basically used to isolate these end plates from the electrical circuit. And then what we have here is this is the copper plates, as I mentioned. These are the current collectors, and this is how they are placed together, and we have the electrical connections at the center here, or this between these two plates. So what we have here is the monopolar plate. These are the monopolar plates. When it comes to stack, it is basically the bipolar, they become bipolar plate. So we have these channels on both sides. So these are the channels which basically take the fuel. This plate happens to be on the hydrogen side. The hydrogen can be supplied from this inlet. Once it enters these channels, we have this diffusion layer right here itself, and then the gas diffuses and reaches the catalyst for the hydrogen side. When it comes to oxygen side, we have a similar construction, and we can see that this oxygen or air in some cases can be supplied to this fuel cell. Once it enters this inlet and it passes through these channels, unused gases can be taken out in both the cases, whereas the gas, while it flows through these channels, again diffuses through the this diffusion layer and reaches the catalyst layer. We also have, like I was mentioning, this is the membrane electrode assembly. As we can see, this is the commercial Nafion membrane, and we have this one as the carbon paper, which is used as a gas diffusion layer. So, it is highly porous in nature. The typical porosity of this gas diffusion layer is around 70 to 80%, and on this diffusion layer is on the both sides, and we have this catalyst coated in between this diffusion layer and the membrane. So, that is how the fuel cell is constructed, and we have typically this gasket. This is a Teflon gasket. So, this is how it is basically put up. Just to avoid any leakages in the cell. So, approximately the gasket is put up like this on both sides, so that there is no leakage that the cell faces when it is brought to operation. So, that is how a typical fuel cell looks like. This is merely a representation. We can have different configuration of the fuel cell or the structure as per demand. So, when it comes to stacking, the single fuel cell looks pretty simple in structure, but when it comes to stack, how does it look like? So, fuel cell stacking. So, all of us know how batteries are basically stacked together. So, in typical we have, let us say, toy. So, basically we have this battery wherein the anode and cathode of batteries are connected, right. So, this is the anode of this battery, this is the cathode of this battery, and so on and so forth, they are connected. In similar fashion, the fuel cells or even the electrolyzers are connected. So, how does it look like? So, let me draw this. So, this is my monopolar plate. On one side I am going to draw it for a stack of 2 cells, so that it becomes easy for everyone to in terms of understanding, and I am slightly going to show the dismantled views. So, this is the monopolar plate for the one cell, then we have the gas diffusion layer. I am only going to show the important parts, so I will probably skip the gaskets. So, this is my membrane electrode assembly of first cell. Let me call this as MEA1. So, this is your electrolyte and this is anode and cathode. So, somehow we supply hydrogen on this side, and once it enters those channels, hydrogen can then be supplied to the diffusion layer, and through diffusion layer it will reach the catalyst site or catalyst layer, and this is our diffusion layer. On both sides. Yeah. So, we know what reaction takes place at the anode of first cell. So, let me write that. At anode we have H2 getting oxidized to protons and electrons. So, let's also draw the bipolar plate. Now, this side faces the I am also going to draw the side that faces the anode of the second cell. So, this is my bipolar plate, which has got channels on the both sides. Then we have the membrane electrode assembly for the second cell. So, this also becomes anode and this becomes the cathode, and then we have the monopolar plate for the second cell. Right. Let me underline the diffusion layer. So, what happens is we supply hydrogen to the first cell, and on an anodic side we also need to supply hydrogen to the anode of the second cell. So, somehow using some case this is hydrogen which is basically in input to the anode of the second cell. So, once it reaches, it is taken out. So, this side is taken out. This is unused hydrogen. Similarly, we have arrangement to take the hydrogen out from the first cell. So, this is unused hydrogen, this is also unused hydrogen. Then we have oxygen being supplied to the cathodes of the both cells. This is oxygen, and then we also have O2 here. We also have to ensure that there is no mixing. This is unused, both of them are unused and they are taken separately. They are ensured that they enter the respective chambers of the cells and they leave those chambers without getting mixed. And that is one of the reasons why bipolar plate makes a very significant contribution in the stacking of the cells. So, what happens is, how does this stacking work, or how does fuel cells, when they are stacked together, they work? So, when we have hydrogen supplied to the first cell, it enters these channels and then it enters the diffusion layer, and at the catalyst layer the anodic reaction takes place. Similarly, when it comes to the cathode, this is our MEA2. So, similarly, oxygen for the first cell, when it enters through the dedicated channels, it enters the diffusion layer and then reaches the catalyst layer, and then at cathode we have the same reaction that we have studied before that takes place. Half mole of oxygen plus 2 moles of protons plus 2 moles of electrons, that give product water. So, this reaction is anyways going to take place. Let us come back to the cathodes and anodes of the first and second cell in a minute. What happens when we have the oxygen supplied to this cathode of the second cell? It is a typical cathodic chamber, and then once the oxygen is supplied to the fuel cell on this of the cathode of the second cell, we have the typical cathodic reaction taking place. Now, the question arises, how are these cells connected electrically? So, as we can see, once we have the anodic reaction taking place in the first cell in the anodic chamber, we get the protons generated. So, those protons travel through this electrolyte, that is membrane, and they reach the cathode. Electrons, they get into the monopolar plate of cell 1, and that is where the electrons are taken out. If we have the current collector takes care of the transfer of electrons in the external circuit. Similarly, when we have the second cell in the cathodic side, when we have oxygen supplied, we also have these electrons coming from the first cell, and then they reach the second cell of the cathode of the second cell. We have this cathodic reaction taking place. Now, we have oxygen, we also have electrons. Where do we get the protons from? So, we have already supplied the hydrogen to the anode of the second cell. So, here the similar reactions take place, that is the anodic reaction, and protons are generated. So, at cathode we get the electrons from the external circuit, we have the oxygen supplied, and we also get protons from the the anode of the second cell. So, that is how the cathodic reaction at the second cell also gets completed. What is left here is how does the cathodic reaction of the first cell take place. So, if we look at this first cell, we have this protons coming from the anode of the first cell. The electrons are already out in the external circuit. In order to process this cathodic reaction at the the cathode of the first cell, it needs or it sort of electrons only, and those electrons are basically received by, or they are basically given by the anode of the second cell. So, when the anodic reaction of the second cell gets kick started, then we have these protons, they travel through the electrolyte and reach the cathode of the second cell, whereas those electrons that are generated will travel back in the bipolar plate and they will reach the cathode of the second cell, sorry, the first cell, and that is how the the electrical requirement of the cathodic reaction is completed, or that is how it gets completed. The very first, or rather the basic assumption that we need to make here is both of these cells are expected to perform significantly in an equal manner. That means the power output from the one cell is almost same as that of the power of the output of the second cell. In other words, if we are drawing x amperes of current from one cell, as the current is going to remain same in both of these cells, the potential is also expected to remain same. There could be few differences in terms of millivolt, that is should be okay, but by and large the operating potential of the cell also should be same, and that is the way we can say that both of the cells are performing well and there is no discrepancy in terms of their power outputs. So, how is the electrical circuit of this cell? As we can see, this is our cell 1, which has got E1 as a potential, and then we have second cell which has got E2 as a potential, and we have the same current flowing in both of the cells. In other words, when I want to find out the power output of the entire stack, it is basically I times sum of the both potentials of the both cells. So, that is how we can find out the total power output of the cell. And the reason why fuel cells are put up in series combination instead of parallel in a given stack is primarily because there is as we have seen earlier, if the area of the size of the electrode increases, we can also expect the current to increase proportionally. So, for typical areas of 300 or 400 centimeter square, we can expect current of roughly 300 amperes of current. So, let me give this an example. So, if we have the electrode of 300 centimeter square, we can expect a current of around 300 amperes or even more. So, in other words, if we have one cell of the stack that is giving output of 300 amperes and the potential is around, let us say approximately 0.5 amperes. So, if you look at these numbers, the current is huge, the current values are more. However, the potential that the cell is operated at, that is pretty low, and that is one of the reasons why the potentials are added up instead of current. And in order to do that, the cells are arranged in series combination, they are connected in series combination, so that the net current that is flowing through the circuit remains the same and the voltage gets added up. So, if you have 10 cells in this stack, so we can simply find out the power of this stack as 10 times the current times the voltage, provided the voltage of all the cells are same, or I can even generalize this as I times the current that times the sum of all voltage or potentials of all the cells. So, that is how we can find out the power output of the stack. Okay, another important aspect that we can go through is the triple phase boundary. Which is also written as TPB. So, if we look at the fuel cell or the electrolyzer, as we have already mentioned, the catalyst layer is somewhere at the interface of the electrode and the electrolyte on the both sides. This is our catalyst layer. Catalyst layer. Since all the reactions take place at these catalyst layers, it is very important to understand what is the chemistry behind getting those reactions at these layers. So, if we zoom in this areas, let us say I zoom in here, I see that it is a very at atomic level we have the catalyst put up like this, and these are the let us say the catalyst is, let us say for example platinum. So, the platinum nanoparticles are put up here, these are all platinum nanoparticles, and this side is your bulk of electrolyte, and this is where your this side will be the gas diffusion layer. So, the reactions that whatever we have mentioned, for example, it could be hydrogen oxidation, or it is the oxygen reduction, these reactions take place at this triple phase boundary. So, what is this triple phase boundary? As the title says, there are three phases that need to get involved in order to have this reaction or any reaction possible. So, as we know, any material will have typically three phases, that is solid, liquid and gas. So, all these three phases, if they are present with respect to different materials at this interface, then and then only the reaction has high probability to initiate there. So, what is the solid phase that we expect at this triple phase boundary? Solid phase means the catalyst is to be present. In other words, if you have a catalyst nanoparticle present there at a particular location across the electrode surface, then the first criteria is met. The next is the liquid phase has to be present. Liquid, in other words, is the electrolyte is to be present, and electrolyte can be, as we have seen earlier, it can be liquid electrolyte, it can be solid electrolyte as well. So, the electrolyte has to be present, and the third and the very last phase or rather important phase is the gas, which in other words means the fuel has to be present at that particular location. So, if you are interested in this location in particular, and if hydrogen once it reaches at this particular site, in other words we have the gas, that is fuel present at this location, we also have the catalyst present there, and this electrolyte, when we fabricate the electrodes, which we will see in upcoming lectures. So, this electrode has got the ionomer present, and this ionomer basically acts like a pathways for these protons to flow from the catalyst layer, catalyst location to the electrolyte, to the bulk of electrolyte. So, in other words, the electrolyte is also present at these places, and that is how the reaction will get complete or it will get initiated, or provided these three things are present at a given location. So, catalyst basically will catalyze the reaction. Once the catalyst has catalyzed the reaction, the protons and electrons, in case of anodic reaction, let us say, the protons will pass through this small pathways, or this is the ionomer basically. Ionomer is the liquid form of the electrolyte itself in some proportion, and this ionomer takes care of the carrying the proton from the reaction site to the bulk of electrolyte. And since we have all these phases present at this location, we can have or expect high probability of this anodic reaction to take place here. If any of these three is absent, for example, let us take this location wherein we have hydrogen reaching the catalyst site. So, we have the catalyst present, we have the fuel present, but unfortunately we do not have pathways very near to this catalyst site that will take the proton from the catalyst to the bulk of electrolyte. Since it is not there, which is primarily because of the fabrication process of the membrane electrode assembly, we can say that the reaction may not proceed here. So, it is very important that we create this triple phase boundary, and that is one of the reasons why fabrication of membrane electrode assembly, or which is also called as heart of the fuel cell, makes, or it is of paramount importance that we fabricate it with utmost care and attention. So, in next class we will see how these electrodes are fabricated and how these membrane electrode assemblies are manufactured. With that, I thank you.